Okay, so we're going to talk about solubility today. It's real straightforward. You've already talked about it before. It's like we are good to go. Okay, the big thing is like dissolves like. Okay, so typically polar things dissolve in polar solvents, and nonpolar things dissolve in nonpolar solvents. Okay, molecules with similar intermolecular forces will mix freely. So, like ethanol and water are miscible in all proportions. You haven't checked that out, have you? Because you know you can only drink that. Over 21. Okay. Well, why does it mix freely in all proportions? Because it's a small molecule and they both do hydrogen bonding. They have similar intermolecular forces. That's how come. But not everything that can do hydrogen bonding will mix freely with water. Not everything. Okay, so why would that be? Well, that's what we're going to talk about. Okay, so are y'all seeing red lines?
Yeah.
From the last slide.
Yeah. Lord have mercy. I don't know what else to do. What? Oh my gosh. Okay, so here is some kind of ion, and here's water, and the water has negative ends and positive ends. Okay, so the oxygen of the water will be where there's high electron density, and the hydrogens are where there's low electron density. So when you put something that's ionic, like salt, in water and you dissolve it, the negative parts of the water surround the cations, and the positive parts of the water surround the anions. Okay, so that's how it works. And you probably talked about that. Remember that it is 3D. There you can have molecules going on these sides too. Oh, let's see what happens. I'm a little concerned. I have writing to do. Okay, if you take a polar solute, and you put it in a nonpolar solvent, so that's what we have. So your nonpolar solvent does not have the variation in the plus and minus like polar solvents do. Okay, you can't break apart the intermolecular forces, so it just globs. So if you tried to dissolve salt in gasoline, gasoline's very nonpolar. It's just not going anywhere. Okay, ever tried that? Good, because I don't know why you would have. Okay, now what if you have something nonpolar and you just try to dissolve it in something nonpolar? Okay, so this is a long chain alkane. Remember, alkanes are all carbon-hydrogen bonds, all single bonds. Okay, so here's a long chain alkane, and we're dissolving it in something like gasoline. Okay, it will dissolve because the attractions of the solvent are going to be the same or similar, pretty much the same as what your nonpolar compound is that you're trying to dissolve. Makes sense? And there's a lovely little picture of it dissolved. Okay, now what happens when you try to dissolve something nonpolar and something polar, like water? It hangs together. Okay, the nonpolar areas do not want to go by the water. They want to stay by the things that are similar to them. So it's very hard to break it up. All right, so anybody ever use vinegar and oil for salad dressing? Okay, and what do you do before you use it? You shake it up and try to get it kind of mixed so you get it all over your salad. But when you leave it sit, what happens? It evaporates back out because it never dissolves. One thing does not dissolve in the other. Okay, so gasoline or petroleum is a really good example because it does not dissolve in water. So what happens when there's an oil spill? Like, yeah, it's like the oil is everywhere, but where is it? It's sitting on the top. It's not dissolving in the water. Okay, and then we have to deal with it. think they'd make the ships better. I don't know. All right, so here's alcohols
Colored
in
water
water.
is added to ethanol, butanol, and hexanol. Water is miscible in ethanol, but not in butanol and hexanol. Butanol has a shorter carbon chain and is less hydrophobic than hexanol. This causes butanol and water to separate more slowly.
You have them on this slide.
I have what?
You have them on the slide.
I have.
The molecular formula.
I do?
Yes.
It's like it didn't come up before the video? Oh, why? It was set that way.
You still have a red dot down on the bottom left corner too, where you have the eraser. Thank you.
Gosh. Telling you, it's Friday. Okay, so ethanol, butanol, and hexanol. Okay, those were the three compounds in the beakers. They poured in the water that was colored green. Could you see that? Can you see green? Okay, and now you can see that it's separated, right? Okay, so you notice that this one, it separated right away. It never really mixed up at all. This one, ethanol, didn't separate. Remember, ethanol and water are totally miscible in all proportions. Okay, the one in the middle, what did it do? It kind of mixed up, and then it slowly found itself and separated. Okay, the water was what color? Green. Okay, so notice that the water is on the bottom. What does that tell you about the density of butanol and hexanol? They're less dense. Okay, does that make sense? Okay, good. All right, so what is different about them? Well, they all have, I may have to erase on every slide, they all have these, okay, those hydroxyl groups from the fact that they are alcohols. We already mentioned that one. What can the alcohol part do with the water when you pour it in? What can it do? Why would it mix up? Right, and what's that called? Hydrogen bonding. That's all I was looking for. Hydrogen bonding. Okay, now what's different about them is this other part of the molecule, this part. This part is made up of carbons and hydrogen groups. Those carbon-hydrogen groups are nonpolar. They do not hydrogen bond. Agree? So what happens is there's like a little battle going on in the molecule. There's a nonpolar part and there's the polar hydrogen bonding part. And the hydrogen bonding part says, oh my gosh, I want to bond. I want to dissolve, okay? And the other part says, no. And so you get to a point where the OH doesn't win, okay? The nonpolar part wins out. And the battle is really bad in the butanol because it's trying to dissolve, okay? And then it just can't, all right? But in here, oh, I missed that CH2. I'm sorry, guy. Okay, so on that one, it's so big that there's no way that it will bond. It will be dissolved at all. You won't even have a time lag on this one. And if you get any bigger than that, you won't either. Okay? All right, does that make sense? It should seem, I hope, kind of logical. I really like that little video. I was worried about this. All right, look. Something worked. Okay. So, I gotta click first. Okay, melting points. Alkanes have soft, low melting materials. Good example of that is waxes. Waxes are very long chain alkanes. Okay, and they have low melting points. Alkanes, it's an interesting fact that alkanes with even numbers of carbon atoms melt slightly higher than those with odd numbers of carbon atoms. Okay, has to do with how they can line up. Isn't that wild? I thought that was really wild when I learned that. Okay, so here are some ethers. Ethers are compounds that have okay, remember alcohols had an OH. Ethers have 2 carbons on either side of the oxygen. The 2 groups do not have to be the same. Like on this first example, they're both the same. They both have 1 carbon. On the second one, we got 1 carbon, and then we got 2 carbons. So the way that we designate that with those R's is a lot of times we put that. Make it like R prime. That means that they can be different. But they cannot be a hydrogen. If one of them is a hydrogen, it's not an ether, it is an alcohol. Okay? So here's the ethers with different numbers of carbons. And this is their solubility in water. You'll notice that the littler ones are a little more soluble, and then as you get larger, they just become totally insoluble. Why would the little ethers dissolve in water at all? They don't have a hydrogen on that O. Their what? Yeah, their weight is little, but why do they dissolve in water? Yeah, the oxygen is still polar. Okay, it still is going to have more electron density. So it can hydrogen bond with the water. Okay, even though those 6 hydrogens on that one cannot. Say it makes sense. Okay, just kind of an extension of what you already know. Okay, here's alkyl halides. Alkyl halides are compounds that have 1 or more halogen. Okay, and you'll see that the solubilities change as the halogen gets larger and less electronegative. Okay, so but by the time you get to 4 carbons, they're all insoluble. This is where they vary, is in these little ones, a little bit. Okay, why would alkyl halides, the little ones, dissolve in water at all? What can you tell me about this bond right here? What can you tell me about that bond? Polar. It's polar, okay, and it's polarized towards the towards the halogen. So this is going to be the negative part. So it's going to be being surrounded by the hydrogens of the water, okay, which is why it'll dissolve. But when the nonpolar part gets bigger and bigger, it makes it less and less soluble, okay, because the nonpolar part now is winning, okay. The nonpolar part is often referred to as the hydrophobic part of the molecule, and the other part is the hydrophilic part, okay. So hydrophobic means it what? Fears water, basically, okay. So it does not want to be in the water, and the hydrophilic part loves the water, okay. All right, how did I know that was going to do that? Oh my God. You know this means too that when I post the complete slides, they won't have any writing on it. So make sure you get the writing part down. All right, we already talked about electrophiles and nucleophiles. Electrophiles are electron loving. They're generally positive or in need of electrons. Nucleophiles donate electrons. They are negative or have electrons to donate in the form of double bonds, triple bonds, or lone pairs. Okay? I'm not going to write anything. It'll make my life easier. I don't have anything to write. But we're going to look at an example. Okay. Identify the electrophile and nucleophile in each of the reactions shown below. So I don't expect you to know what's going to happen. We're going to get to that. But I want you to look at what happened. So look at your two starting materials. This plus this. And here is what we got. Okay? So when you look at that, analyze it. What changed? What is different? The what? The what bond? The double bond. Okay? The double bond was on the, from between the C and the O. Is there a double bond between the C and the O now? No. Okay. What else can you tell me? Anything else changed? What's different? The charges. Okay. What about the charges? This oxygen is neutral, and now it's negative. What else? Wasn't this one negative? And now it's neutral. Do you believe that? If you don't believe it, calculate it out. Double check. Okay. So which one up there do you think is the nucleophile? Who donated electrons? The one on the right. Who is the electrophile? Who accepted the electron? The one on the left. All right, now, I was worried it was the other way. That's why I didn't click already. Okay, and if you are going to draw the arrows, you would start at high electron density, and we went here. Can we stop there? No, because that carbon would have how many bonds? 5. Does carbon get 5 bonds? You should all resoundingly say, no. Okay, now where do I go? Yes. So the electrons in this lone pair are now where? In this bond, right? Okay, and the electrons that were in this bond are now where? Up here. Does that make sense? Okay, now look at the one on the bottom. What do you think about the one on the bottom? Not much? Okay, analyze it. I know that you've never seen it before in your whole life. If you have, I'd be like shocked. Okay, so what do we have here? What changed? Tell me what changed. The double bond is no longer there, right? Okay, what else?
Charges changed.
Charges changed, okay? What specifically?
Carbon's positive and the boron's negative.
Over here, okay? And in the beginning, they're both neutral. Okay, whoa. All right, so which one do you think is the electrophile?
One on the right.
Who accepted the electrons? And who gave the electrons? This thing. Yeah, that thing with the double bond. See how we got that? Okay, if I was to draw my arrow, how would I draw it?
Double bond for the boron.
Yeah, we're just going to go from here to here. Are all those fluorines on that boron over there? Yep. So all we have is one bond. Okay? Now, electrophiles are also referred to as Lewis acids. Lewis acids are, what's the definition of a Lewis acid?
Electron pair acceptors.
Electron pair acceptors. Do you see that the boron is accepting electrons? Okay, who is the Lewis acid on the top one? The one on the left or the one on the right? Left. You see that it is accepting electrons. Okay, that's how you decide. And here we go. All right, hang on. I'll fix this. And then you all can do the deal. All right, can you read it now? Did I miss one? Oh. Oh, I see. Okay, is that it now? Yeah, I didn't see that. All right, let me go to there and see if that's going to work. And I'll count while you all are. I'm getting 24. Does everybody have their clicker?
Someone just went to the restroom.
I know I was counting her, and that gave me 25. And 29 minus 5 is 24, right? Maybe I can't count. Okay, make a pick. Try something you've never seen before, okay? But you have to decide what happens. So you have to look at it and analyze it. They're still bleeding. All right, can I get to 23? Okay, that's everybody except our person who ran to the bathroom. Sorry. Okay. Who is accepting electrons? That's the Lewis acid. Okay, so if you look at what happened, your oxygen is now attached to the aluminum. And where did the electrons come from? The oxygen, one of these lone pairs, and it went to the aluminum. So who accepted the electrons? This one. A gave the electrons. There's going to be compounds that can be Lewis acids and Lewis bases, either or, okay? Don't just look at this and go, oh, this has that C double bond O. Last time it was the Lewis acid, okay? You have to look at what happened in the step, okay? And this would be like a step of a whole reaction. This is just a step, okay? I don't expect you to figure out the steps yet. Just analyze them. Okay. Did I get it all? Okay. I'm going to get my exercise this morning. Okay. Okay, so what is Arrhenius acids and bases? What are acids? Proton H plus donors. I'm not even going to say proton yet. Okay, what are bases? Hydroxide ion donors. Okay. There's acid and base. Okay, what was the next one? Bronsted-Lowry. Acids are, okay, proton donors, and bases are proton acceptors. And the last one was Lewis, and acids were, yes, electron pair acceptors, and bases were electron pair donators. Donators.
So hydrochloric acid is still, is it?
It's an acid in every definition. Yeah, it's an acid in every definition, because that H plus will accept an electron pair. Okay, so H plus and OH minus are acid. H plus is an acid and OH minus, hydroxide ion, is a base in every definition. Okay, so if you got mixed up, pause and go, wait a minute, is it acceptor or donor? Sit and look at H plus. It's an acid in every definition. OH minus is a base in every definition. When I figured that out, I finally got them right. Okay, like, because I would get them mixed up too when I was a student. It wasn't that long ago. Well, okay, explain why gasoline does not dissolve in water. All right, I've only got 23. Did yours go in? I'll make sure it counted you as here, even though you had to miss that other one. All right. I only got 23. I'm
I
gonna
get
put-
24.
all right. Okay. Yep, it's D. Like dissolves like, and they aren't like. They're different. And water is polar, and gas is nonpolar. Okay? That was your gimme question. It failed me. How about that? I cannot win, I tell you. Okay. All right, so we classify compounds by functional groups. Okay? The functional group is the part of the molecule that takes part in reactions. It's the party part. Okay? It's the cool part. How do you know it's a functional group? It's not carbon or hydrogen. Carbon and hydrogen are boring. Okay? I mean, we need them, but, you know, they're kind of boring. They don't get to play around very much. It's the other elements, oxygen, nitrogen, halogens. They get to do all the fun stuff. So that's what we're going to look at. We have three broad classes. One is hydrocarbons, compounds with oxygen, and compounds with nitrogen. We will talk about the halogens too. Okay, so hydrocarbons are compounds that only contain hydrogen and carbon. Get it? Isn't it nice when it makes sense? If only it all did that. All right, so here we go. Hydrocarbons, alkanes, I've already told you about, are all single bonds. All the carbons are sp3 hybridized. All single bonds. Okay, here are cycloalkanes. All carbons are sp3 hybridized, but they make a ring. And I think I showed you that a little bit already. Okay, here are alkenes. Alkenes contain at least one carbon-carbon double bond. So those carbons are sp2 hybridized, but you can have a whole bunch of other ones that are sp3 hybridized. So for example, I know I'm going to have to erase it. Okay, I'm going to go like this. Okay, that compound is an alkene. It has how many carbons total? 7. Good. I'm making sure you're reading the structure right. Okay, how many carbons are sp3 hybridized? 5. Good. And how many are sp2 hybridized? 2. You got it. Okay, alkynes. It takes all kinds to make the world. Okay. Some carbons are triple bonded. You have a double, you have a triple. This is a triple bond, okay? When a carbon is triple bonded, it is what hybridization? Sp, okay? All right, so I will give you one of those. I'm probably going to have to erase that one quicker. Okay, so how many carbons are in that one? 6. Okay, how many are sp hybridized? 2. Everybody see that? Do you need me to label them? I just have to erase it. Those 2. What are the other carbons? sp3. Okay, sp3. Okay, notice that that compound is considered to be an alkyne, not an alkane. Okay, as soon as you put in a double bond or as soon as you put in a triple bond, alkane is out. Okay, you only have alkanes when that's all you have. Okay, alkanes are boring. They don't hardly do anything. We use them because they burn real well. And we get a lot of energy off of burning them. So gasoline is alkanes. Natural gases, alkanes. Okay, that's what you're using to heat your house and stuff.
You can't have like a triple bond and a double
Yes, you can. We're going to get to that. Yes, you can. Okay, I'm going to erase this. You can have them all mixed up. Okay. Well, let me get everything on this slide. Okay. Aromatic compounds contain a benzene ring. Now, have you heard of benzene? Okay, at least heard of it, even in whatever context, okay? It's not as poisonous as everybody makes it out to be. It's not like you're going to use benzene in the lab and we're all going to die tomorrow. Okay, that is not going to happen, okay? But you don't want to be drinking it, okay? It probably doesn't taste good anyways, all right? But you don't want to be washing your hands in it. And that's how people got leukemia from benzene, was they were washing car parts in benzene, like to clean the oil off. And when they did that, it was forced to go through their skin. If you're in the lab and you spill a little bit of benzene on you, it's going to evaporate before it goes through your skin. We're not all going to die of leukemia, I promise. Okay? If somebody does, I'm going to feel really bad. But no, you're not going to get it from the benzene. I'm going to feel really bad. Okay. No students from the past have come back and said, I'm dying of leukemia, and we traced it back to benzene in the lab. No. Okay. We used it in one lab. Yeah, I'm telling you. It's pretty scary. All right. So let me show you what a benzene ring is, though, because that's the more important part. Oh my gosh. Okay. A benzene ring is a 6-membered ring, and it has alternating double, single, double, single, double, single. Okay. I want you to tell me what the hybridization of those carbons is in the benzene. What is the hybridization of that carbon? What do you think? Very good. Every one of them is sp2. Okay, we'll talk more specifically about benzene next semester. Okay, we don't even get to that till next week. We have so much to do. Okay, now you can also draw it like that. Do you see that those two things are like resonance structures? Okay, so what you will see a lot of times when you look it up is this circle in the middle, okay? If you run into that already and not known what the circle was and just copied it, that would have been my advice. Just copy it. Like you had to look up the aspirin has a benzene ring in it, okay? All right, now if you don't remember that from that lab, go back and look again and find the benzene ring, okay? Okay, now what if I have, here we go. That. Okay, let me tell you guys, I can drum till the cows come home. And that happened once. I go outside my front yard, and I just live in Denison. And I'm not even really out in the country or nothing. We go out, and we live near the highway. And this is the big house, and the whole front yard is covered with cows. Like, there's like 8 cows in my front yard eating the grass. I'm like, what? And of course I call, Paul, what do we do? And he's like, oh, I'm going to call the sheriff. So he calls the sheriff, and we had a little Australian Shepherd at the time. Her name was Kira. She'd just been a family pet. He let her out. I said, don't let the dog out. Oh my gosh, she's going to get stepped on. Do you know what she did? She herded him. It was the coolest thing to watch because I'd never seen her do it. She ran around and herded all the cows to the neighbor's yard. It was hilarious. It was hilarious. I was like, oh my gosh. Anyway, apparently there was a ranch a little bit back, and they got a hole in the fence, and all the cows had just been walking till they got to a yard with grass, and they ate it. But anyway, so the cows did come home one time. I'm telling you. Yeah, it was something. And she didn't get stepped on. Yeah. She was a sweet girl. Okay, so I want you to tell me the functional groups in this molecule.
There's an
There's a what?
There's an aromatic.
There's an aromatic right here. Okay? Aromatic. Is that it? No. What else we got?
Alkyne at the end.
Okay, this is an alkyne because it takes alkynes. Okay, what else?
Alkene.
Alkene. Okay? Now, we don't circle the carbons that are left and say they're alkanes. You just have to know they're alkane-like, but the molecule doesn't get classified as an alkane unless that's all there is. Okay? Otherwise, we'd be circling things till the cows came home. Again. Okay? All right, so you only get this if that's all there is. Okay? So if I have this, what do you think that is? It looks like a stop sign, doesn't it?
Cycloalkane.
This is a cycloalkane.
So in the bottom structure, which one holds priority as far as like the naming of it?
Don't worry about that till we do the naming. Just chill on that for now.
Okay.
Okay, yeah. Yeah, the whole naming thing is its own little ball game.
Okay.
Yeah, that's chapter 3. Okay, and we're not even going to do all of it. We're only going to do part of it in chapter 3 to get you started. Okay, they split it out amongst all the chapters. I knew it. All right. Hey, it worked that time. I missed one where?
On the right.
Oh. People who watch this video are going to be like, what did they do?
But she's talking about the cows coming home.
Oh my gosh.
Might as well.
They're going, the cows are coming home. Yeah. All right. Density. Alkanes are less dense than water. Alkyl fluorides and alkyl chlorides are less dense than water. But that's only if you only have one. And then as you add more halogens, the density goes up. Alkyl bromides and alkyl iodides are more dense than water because they're so much bigger. Okay? Alkyl iodides are deceptively heavy. Okay? This compound is a liquid, but you pick up that little bottle and oh my gosh, it's quite a bit heavier than you expect it's going to be. Okay? Kind of like mercury in the bottle, except mercury's even heavier. Okay, compounds containing O. Yeah, well. I was too fast. I'm sure it was it. Okay, so what have we got with oxygen in it? You already know some of them. Alcohols, they contain OH, hydroxyl groups. Okay, ethers contain 2 alkyl groups bonded to an O. Remember, an alkyl group is a carbon-hydrogen group. Okay. Aldehydes and ketones. This is one I haven't told you much about yet. Okay, so an aldehyde and a ketone both contain this thing, C double bonded to an O. That is called a carbonyl. You don't know how hard it is to not say words I haven't defined yet. Okay, is a carbonyl, okay? The difference between an aldehyde and a ketone is an aldehyde has a hydrogen attached to one side. Okay? This, I'm going to do that, has 2 R groups. The R groups can be the same or they can be different. Bless you. All right, so here we go. Is that an aldehyde or a ketone? Okay, well, you find the carbonyl. It's right here. Okay, what is this? A carbon. What is this? It is a, do you notice that ketone does not have a Y in it? Okay, doesn't have a Y in it. It's just K-E-T. Not key, K-E-Y. I see that all the time. Okay. What about this one? Is that an aldehyde or a ketone? What? It's both. Okay, I was being tricky. Okay, so show me where the ketone part is. Which one? There's two. This one, right, is the ketone. You know I have more words on here, and I am going to have to erase all this. Okay, so what about this? That's the aldehyde. Okay, and I want to show you, notice aldehyde, hydrogen. Get it? Yeah. I don't know how you're going to remember ketone, but you know. Practice. Okay, now, another way that we draw those. Do you remember when we talked about the condensed formulas and we smashed them all down? Okay, so you can write it like this, the CHO. So I could have drawn that compound like this, with a CHO instead of drawing it all out. CHO means aldehyde. Okay, and that H right here, that's the hydrogen that makes it an aldehyde. Okay, do not get that confused with an alcohol because it kind of looks, I mean, you might be flipping the OH around. Okay, be careful about that. Okay, all right, now we know what's going to happen. I knew it. Okay, so apparently I need one slide for each. It's probably what I should do, but you know, it's a little late for that. Okay. Did I get most of it?
Yeah.
Most of it. Got a little dot there.
Where?
Right there in the middle.
All right, carboxylic acids. We already talked about them too because of that one special carboxylic acid, acetic acid. Okay, so here is acetic acid. Okay, and remember what the CO2H means. It means a C double bonded to an O and also attached to an OH. That's the carboxyl group. That's this. Okay. Here's another one. Butyric acid. It smells like rancid butter. And if you have never smelled rancid butter, you don't want it. Okay, so just keep that in mind. So like we're not going to use that in lab. I'm sure Jay-Z won't use it. Even in his old age. Okay. Oops, this is what I need. Okay, and the last one that we're going to talk about is esters. Just so you know, there are other functional groups besides all the ones I'm showing you. I'm showing you all the common ones, okay? And we may mention a few of the other ones coming up, but okay, so here was acetic acid when there was an H here. Take that H away and put another R group. That's an ester. Okay, so this compound no longer has that acidic proton. Okay, you see that it's gone. Okay, okay, what about this compound? What about that? What do you think that is? Is that an ester? It's not an ester because these carbon here has to be attached to a double bond O and the O. Okay, this carbon here is attached to the double bonded to the O, and then it's attached to another carbon. This is not an ester. Okay, what is it? It's a what? There's a ketone. Is that all it is? What about this? What is that? What is that O attached to? This carbon here and this carbon here. So what is that? Ether. So this compound has a ketone and an ether in it. It is not an ester. Okay? Is this a benzene ring? No. It has to be double, single, double, single, double, single all the way around, or it has to have that circle in there, which means double, single, double, single.
I don't really understand how that's ether, because I thought an alkene was the triple bond.
An alkene is a double bond. An alkyne is a triple bond.
Wait.
Two carbons. These are not two carbons. This double bond is two no.
Yeah, but like the alkene group in the ether definition.
The alkyl group,
Yeah.
yeah. You have this one and you have that one. You happen to have another functional group in there. You can have multiple functional groups in a compound. Okay? All right, so on Monday, we'll do the nitrogen ones, and that's really the end of the deal. Okay?
So we're just finished chapter 2,
Yeah.
not 3? Like
We'll
those
start
three.
chapter 3 on
Okay.
Monday, but it won't
All right.
be on the test.
Okay.
Okay.
Okay, so now what I don't understand is like an alkene group.
An alkyl group is a carbon hydrogen group. Okay? So you can have an alkene. And an ether. This is the alkyne. And this is the ether.
Yeah, but how in that picture where's the triple bond?
There is no triple
Well,
bond.
that's what I don't understand. Is how can you have an how's that an alkene? Or
It's
how's
not.
It,
If this is a ketone
yeah,
and an ether.
yeah, but the ether has to have two alkene groups.
No, alkyl group.
Alkyl,
That
yeah.
just means you have to have a carbon here and a carbon here.
Okay.
That's all the ketone that means. You just have to have a carbon here and a carbon here. You don't have to have a triple bond or a double bond. You just have to have some kind of carbon attached to them. Okay, yeah. Here, this is your pen. Don't let me run off with it. Okay, yeah, you just have to be able to pick them out. There's going to be compounds that are going to be uber complicated, which I'll show you on Monday. We'll practice on Monday, so maybe that'll help you get it then. But you have to learn what to look for. Carbonyl, carbon-carbon. Carbonyl, carbon H, that's an aldehyde. Carbonyl OH, that's a carboxylic acid. Doesn't really matter what the rest is, because you can be all mixed up. Does that help you?
Yeah, I just like didn't. I guess I was just associating the alkene group with the other.
The
page.
alkyl group
I
with
can't
the
say
other
it, yeah.
groups, with the other functional groups. Yeah,
Yeah.
no.
Yeah, that's what I was doing. Okay.
Okay.
Right.
What you need? Angelica?
I wanted to know since
Oh.
the afternoon if
Okay, that's right.
should I just
Well, what
Take it
time
in
is
the
your
morning.
class?
2 to 4:30?
Yeah, but I don't want you to miss the review at 11.
Yeah.
You don't need to miss the review.
Yeah.
Can, in your class at 2, if you do it at right after class, you don't get
Okay.
lunch? It gives you 2 hours, 12 to 2. You could eat while you take the test.
Okay.
But I
I
could
think that
put
would
you
be
in here
better.
and have you do it. Yeah, because I don't want you to miss the,
Yeah, I don't want to miss it either, but
Yeah.
I was wondering when I would be able